Okay, good morning and welcome on behalf of myself, Andrea Torsello, and all the other general chairs, Marcello Pellillo and Luca Rossi, and the SPR and SSPR chairs, Battista Biggio and Antonio Robeschelli, the honorary chair, Edwin Hancock, and the local chairs, Filippo Vergamasco and Sebastiano Vascon. I'd like to welcome you all to SSPR 2020. In which in this new normality that we have now with this online only mode that we hope will be a one-time thing, and really hope we will be able to see each other again, to see one another again very soon, and be able to have normal workshops with all the normal exchanges that happen with it. We're having a very nice workshop with a lot of very interesting papers. If you might have already seen them, we have already loaded them almost all the presentations in the YouTube channel of the conference. So if you go to YouTube, you can at any time look at the full oral presentation of all the papers accepted. And today we will be having we'll be having this 2-day event where we'll be having two keynote speakers, one in the morning CET, Central European Time, one in the afternoon, and around midday we'll have the paper discussion session. The paper discussion session will be organized roughly as opposed to session, in the sense that it will be divided into breakout rooms, one per paper in the session, and at least one person for the one author of the paper should be on the paper's breakout room at all time to discuss the paper. Sharing will be available, so if you want to have any visual aid, do use them, but be wary that people can come in and out of the breakout room at any time. So treat it as you would treat a sort of poster presentation, but online. As I said, we're having, given the difficulties, a very successful conference. We had 81 very successful submission part of the conference. We had 81 submissions. We have accepted 35, but we actually had submissions from 29 different countries, spanning basically every continent except Antarctica. So definitely, still, SSPR is showing that its community is very international, and it's capable of having people having submissions from all around the world. We had peak submissions. Actually, the top country for submission this year was Russia, although the top acceptance was the top acceptance was shared between Italy and China. So that's all about admin bits. If you have any question or any problems at any time, please contact either me or Luca Rossi, Filippo Vergamasco, or Sebastiano Vascon, that will help you at any time. Today, actually, I'm very happy to be able to introduce the first keynote of the day. The first keynote speaker is Nicholas Carlini. Nicholas Carlini is a research scientist at Google Brain. He's very well known in the community for his work on the security and privacy of machine learning, in particular with this idea of an adversarial setting. And he's also have very recently received Best Paper Awards from ICML and IEEE S&P. He's a Berkeley candidate, Berkeley graduate, both BA and PhD, fairly recent PhD in 2018. And he's agreed to very kindly to be with us today, although the time difference means that now it's about 2 o'clock in 2 o'clock at night. What is that? So let's give a very warm welcome to Nicholas for his talk. Thank you.
Thank you. Let me share my screen. Okay, everything okay?
Yep.
Very good. Yes. Yeah. So thank you for having me. I'm excited to be here, even if it's maybe a little bit late at night for me. But no, this is great to come and talk. So I'm going to give a talk that's on deep learning and why it's still not robust for various different definitions of robust. This is going to cover two papers that we've recently done work on that we just had accepted at NeurIPS, and we talked about. Maybe you may have seen just last month. So the general setup is that machine learning has seen wildly successful deployment of natural language processing and speech recognition and translation, and in general is now actually being used in many settings. And so it's important that these models are actually able to solve problems in a robust manner. So the one thing I'm going to focus on in this talk is going to be Imagenet classification, just because this is where most robustness research is focused and where we can talk the most rigorously about robustness. And so again, Imagenet classification, neural networks can do basically human levels of accuracy. And so the main question is, are they good in all settings? And the answer here is no. And the common example people give for this is now adversarial examples, which is this property that if you take an image that a neural network gets right, maybe this tabby cat on the left with 88% confidence, you can have an adversarial perturbation that gives you an image that looks essentially indistinguishable to us as humans. But so that this image on the right, the same neural network will misclassify it with 99% confidence as the label guacamole. And to us as humans, these two images are obviously identical, but for some reason, neural networks are not robust to these very, very imperceptible changes to these images. And so what I'm going to talk about today is these kinds of non-robust, the way that neural networks behave in these non-robust robust manners. But also, neural networks have these other failure modes where even in non-adversarial situations, so there was this news article a couple months ago that I found hilarious, where some people decided that they were going to get rid of their camera operators. You don't need camera operators today. We're just going to have an object tracking thing to just follow a game of what in the United States is soccer, but in all of the rest of the world is football. And it decided that the referee's head was what the ball was, and it was just going to follow that around for the entire game, which was not terribly exciting to watch. And there was no adversary. The referee here did not decide that they wanted this to happen. The system just was not robust in some entirely benign scenario. And here the harm was not that great. Some people just couldn't watch the game as well as they wanted, but you still kind of see these kinds of these issues as they happen. So this talk is going to basically cover these two kinds of non-robustness. There's the adversarial kind, where someone is sitting down and deciding that I want to make this system behave poorly. And they're going to maliciously craft, every pixel in order to fool the system. And on the other side, you just have these natural shifts where the system was never trained in the right setting and it happened to do the wrong thing. Let me get started by just talking about the adversarial kinds, where I've done most of my work. And recently, we have this paper with Florian, Wayland, and Alexander that we talked about at NeurIPS, where we looked at a bunch of defenses to try and see how we're doing in this field. So to get started, the definition of these adversarial examples, I think it's nice to sort of just briefly say, like, all we're doing here is we're talking about the robustness of something when there is someone who is intentionally trying to fool the system. And so what we're saying is that we have some neural network, maybe this is some classification function, and we have some regular input X. This is maybe the image of the cat. Well, all we want to do is just find a new input so that the input is misclassified, but that we haven't changed it by very much. Now, there are easy ways to do this, and they're sort of well studied in the literature. And so what we're going to define is, as the important metric, is the adversarial accuracy, which is just the probability that an adversary can succeed at this game that we've just defined here of finding inputs that fool the classifier. So we'll specify some kind of bound, like you can perturb the image by this much. And we want to know what the accuracy is when we have this kind of constraint. So what we did in our recent paper was we took a look at 13 recently published papers, and we tried to analyze them. This is one of the first papers I've written where we had like an actual table of contents because of how many different papers we've analyzed. And the main result is that of these 13 papers from ICLR and ICML and NeurIPS published in 2018, 2019, and 2020, basically all of them were broken. Where broken here means that the claims that were made in the paper are for the most part wrong. In all but maybe 2 cases or 3 cases, we could get the accuracy down all the way to 0, and they were no more robust than a standard baseline neural network that had no robustness intervention on top of it. And so these were papers that, got reviewed, got accepted. Many people worked on them for many months, but on the whole did not increase the robustness on top of just standard training, not doing anything else. And so this is a problem because, we've seen this before. This is not the first time that papers have been broken. We've been doing this for a long time. And it's kind of disconcerting to see that after having been doing this for several years, that again, it's the case that papers go out and try and solve this problem, but by and large aren't able to do anything to increase robustness. And so to give you a little intuition about how it is that we're actually broken, let me give you some visual intuition. So what I'm going to show here is a decision boundary analysis of a neural network. So what I'm going to show initially is we have some image from maybe the CFAR test set, which is in the middle. And as I move along one axis, I'm going to add one kind of noise to the image. And so maybe I have a very noisy image of this dog here on the right. And then as I move along the other axis, I have another kind of noise that I'm going to add to the image, which is maybe this other kind of noisy version of this dog. And now what I'm going to do is every single point, I'm going to linearly interpolate each of these images and then classify them with a neural network, with a trained CFAR model, and ask what the decisions of the model are on these images. And we'll get a plot that looks like this, where this middle region here are all of the points that are classified correctly as dog. And then I have this green region around on the outside, and then this dark blue region as I go farther out. And so you might think that, basically this means everything is fine, because if I look towards the middle of the image, these are all of the points that have very little perturbation being added to them, and they're all classified correctly. So everything looks pretty good here. And let me just do one more thing to this plot that will become useful in a few minutes. And instead of just showing this plot in 2 dimensions, where I'm just showing the decision boundary, I'm going to make it 3-dimensional. And the way I'm going to do that is by adding on to this plot a z-axis, so that the height is going to correspond to the confidence of the neural network in the correct prediction. And when I do that, I move from this plot to this plot here, which if you sort of imagine that you were looking from the top down, would look the same. These 2 plots would look identical. The only thing that I'm doing here is I'm sort of showing from the side that you have the correct class, which initially is this dog class, which is near the middle here. And then as you move out, sort of slowly everything degrades and you become misclassified as other classes. And this is really what you want out of a classifier, that as you add noise, the classifier begins to become incorrect, and we expect this. The problem is that what I've shown here is just for 2 random directions what's happened. But it turns out that for these classifiers, so this plot will spin. Maybe the spinning is showing over the video, maybe not. But this is what happens in random directions, where I just add random amounts of noise to both dimensions. But what happens if I add adversarial noise instead of random noise is that now the decision boundary moves to be almost exactly on top of the origin of this image, where the original image is right in the center, remember. And so what we have is that, again, you can move in the random direction quite far, and you'll go into the green class, and then eventually you'll go into this blue class. But if you go in the adversarial direction, then it's very, very easy to fool these classifiers. So, okay, so this is all what happens in normal classifiers. Again, I can show you this in 3 dimensions, where it starts out with you see the random dimension here, and then as the plot spins around, you can see what happens when you have this adversarial dimension, where you sort of just on the face of a cliff, and because we're in very, very high dimensions, the reason why adversarial examples work in this way is that there is some dimension that we can travel down where we can really just fall off the face of this cliff in order to generate an adversarial example and find a way to misclassify a given input with the neural network. So this is what happens for normal classifiers. And what people try and do is they try and come up with ways to make it so these classifiers are more robust. The problem is that in practice, what actually ends up happening is not making the classifiers more robust. It just makes it a little bit harder to find adversarial examples. And this is something we've been seeing for a long time. And the general way that this happens is that instead, the loss surface just instead becomes something like this. Like it just becomes this really, really jagged and ugly function. And it doesn't like on the whole look all that different if you take the global view. But like we only have the global view as humans sort of visualizing this. If you imagine what like a neural network sees, like when it's doing gradient descent in order to actually try and find which way is down, it sees something much more like this, where what it's trying to do here is to just like, it's on one side of this really ugly cliff and it has to decide which way is down. And so it like takes one step in one direction and now it has to go in the other direction. And so it just sort of makes no progress and spends a whole bunch of time just spinning around in circles. And this really is the problem with what these defenses do, is they make it very, very hard sort of for gradient descent as it's normally constructed to work. But in practice, they're not actually changing the decision of the neural network to make it more robust. And this is, again, is something we've been seeing for a couple of years. Defenses commonly do this. And so the main theme of our paper is to say that one of the problems that these defenses have is that they work against the standard attack. If you were like, take some code and download it and run it that runs attacks, these defenses work. And they do it sort of very well against this setting. But what they don't work is when someone decides that they're actually going to try and break this particular defense. And what's new here is that papers used to be broken in this way too. But they used to not even try and be robust, these kinds of adaptive attacks. Whereas now what we have is we have papers that explicitly claim, in this case, 12 of the 13 that we analyzed explicitly tried to claim robustness to some kinds of adaptive attacks. But when we actually analyzed them in this setting with the attacks that we were able to construct, we were able to break, again, almost all of them. And I'm not going to tell you how we broke these ones in particular, because it really is quite boring. We basically took the 13 papers and just did a one-off attack against each of them. We introduced no new interesting technical ideas. We just used the techniques that were already published in the literature and applied them correctly. And you can tell that it's kind of boring because these plots that I'm showing here look nearly identical for this one and looked nearly identical 3 years ago when I first generated some of these plots. And so the way that we do what we do is essentially we just take this surface here, which is ugly, and on a case-by-case basis, we find out what's making the surface ugly and find some way to smooth it out so that now the function is easier to perform gradient descent on. And now we can move from the blue class to the green class, and everything works nicely. And okay, so let me talk a little bit, instead of telling you like how we actually broke these, because again, it's sort of a case-by-case basis. If you're interested in details, like, I mean, I'm very interested, but I would instead like suggest you to just look at the paper. It's not something that makes great talk content. Let me tell you a little bit about the context of why I think this paper is interesting, and what it says about the community right now. So previously, we would have this thing going where, someone would publish a new idea that was a new defense idea, and then we'd get a new attack idea, and then there would be like a new defense idea and another new attack idea, and then this process repeats. But as I've said, now, and like okay, so like there are lots of like attacks that we've been seeing over the last couple of years, and so like this literature is fairly robust, and I like a lot of it, but the problem now is that now we have these new defense ideas, and the attack idea, yeah, as I've been saying, is just reuse one of these defense ideas. And the way that you know that, like, sort of I'm telling you what actually has happened is, this is one of the reviews we got when our paper was rejected for the first time, where the reviewer just straight up says, this is a bad paper because we're just using existing techniques. All of the techniques we're using exist in the literature, and we're not introducing anything new. And, the reviewer is completely right here. We introduced nothing that was new. We are showing that the field has not advanced to the point where we are able to construct solid defenses that work even against the things that we already know how to build as attacks. And this is, I think, very unfortunate. I was hoping that we would be able to be further along than we are right here. There are some positives, though. The first thing that we're doing much better for robustness in this area is, code at least is always available. It used to be the case that it was very hard to analyze these things just because people wouldn't release source code. In all cases for the 13 defenses we analyzed, there was source code available. And so that made it actually even possible to do the analysis in the first place instead of trying to spend months reproducing each paper individually. And the second piece is we've gone from not thinking adaptive attacks are important and the community just wouldn't try them the first time around to now they're being tried the first time around, but they're not quite being applied correctly. And when we apply them correctly, we can still break things, but at least they're being tried in the first place. And so this is the piece that I want to spend a little bit more time on, is to understand what is it that's different between the original evaluation that was done and the evaluation that we did in order for ours to work and the original paper's evaluation to fail. And basically, we argue the problem here is methodological. And the problem is that when designing attacks, it's really important to aim for simplicity. Defenses might be complicated, and defenses might have to be complicated. It might just be adversarial examples are hard to solve, and you might need something complicated to solve them. But when constructing an attack, it's very hard to distinguish between something actually being robust and the defense just making it hard for one particular optimizer to find adversarial examples. And so by making the attack as simple as possible, it's easy to understand what failures go on and understand if the failure is fundamental or if it's something that can be worked around. So for example, one of the papers that we looked at tried an adaptive attack in their evaluation. And when they did this, they introduced a loss term that was some L1 loss term that asked for an input to be misclassified. This is sort of the standard loss term you have. You just try and make the input be misclassified, and this is good. And then they added on, because their scheme had a detector, they added on another loss term, which has some expectation, and they're trying to bypass the first detector here. And then they added another loss term. And this next loss term is another expectation where they're doing something in order to fool some next detector. And then they added another loss term. And this loss term, again, is trying to fool some other detector. And their final loss, is the combination of all of these with another hyperparameter lambda thrown in, just for good measure. And it's true that you want to minimize all of these things. You want to fool each of these detectors, and you want to try and solve all of this. But you're trying to do this thing also while having two different expectations and another non-differentiable component thrown in the middle of all of this. And just like the number of moving parts here is just really, really high, where it's surprising. Like, gradient descent is not a magic black box that you can throw at anything. Like, gradient descent works in very limited cases. It just so happens to work nicely for neural networks. And when you have loss functions that have two expectations over, various random variables, three non-differentiable components, and a couple different hyperparameters sitting in the middle of everything, it becomes very hard to write these attacks correctly. And so what we do in our paper is we basically throw away like all of the stuff that is like complicated, and we just get rid of all of it. And we say, like, let's just ignore all of that. And let's focus all of our work. Let's just sort of sit down and think rigorously about what is necessary for the attack to succeed. And that's that it has to be misclassified. And so all we do is we just come up with the right way of using this one loss term in order to fool this particular defense. And this is essentially what we do for the remaining 12 other defenses, is we take the original evaluation and we find the one piece that actually mattered for the scheme to be robust. And we put all of our work into making that piece as strong as possible. And we don't waste time on any of the difficulties with many of the other pieces in order to make the attack as effective as possible. Okay, so this is the first piece, where we've seen now that, neural networks still not all that adversarially robust. Of 13 recent defenses we've surveyed at ICML, ICLR, and NeurIPS, most of them are almost completely broken. Now, let me talk not just about this adversarial side, but about something that's maybe a little bit, you might think is something that's easier, is what we'll call natural distribution shifts. And this is another paper. Most of this work was done by Rohan, who was an undergrad at Berkeley at the time, and he did an amazing job on this. And so for this paper, instead of talking about these adversarial kinds of shifts, we're going to talk about distribution shifts that happen in nature, like things that actually really happen in the real world. So let's think for a second about how we want machine learning to work. What we want is someone, like, I want to know what breed some dog is. And I know that Imagenet has 100 breeds of dogs. So I'm going to take out my phone, I'm going to open up the camera app, and then I'm going to take a picture of the dog and run it through a ResNet, and it's going to tell me what kind of dog it is. And this is what we want. Unfortunately, this is not what Imagenet was actually designed for. What Imagenet was designed for was the case where all of this happens, but then you close the camera app, you open up your browser, you go to imagenet.org, you download the test set, you select an image at random, and then you ask the ResNet model to classify that image you've selected at random, and you ignore the real dog. Like, Imagenet was not designed to work when someone takes an actual picture of a dog on their phone in the real world. Like, it's only designed to maximize accuracy on that particular test set. And this is a problem. And there are lots of examples of distribution shifts where we see massive drops because of this effect. So let's try and take some data sets that construct natural distribution shifts. And I'm using the word natural here sort of in a precise way. What I mean by this is there are lots of data sets that exist in the literature which are somehow synthetic. Maybe this means adversarial examples for one instance, where what we're doing is we're taking images that exist normally, but then we're doing something synthetic by running some program to generate some new version of this image, which is now misclassified. But there are other versions of this. There's the common corruptions. There are other kinds of synthetic distribution shifts that I'm not going to be talking about now. What you can think of as natural is, conceivably, you could go into the real world and take a picture of a thing. and get a new distribution shift. Okay, so there are lots of papers that do this. There's this paper that does generates a new ImageNet test set. There's another paper that goes and does the thing I just described actually in practice. They ask people to go out and take pictures of common objects as they exist in the real world. You have these papers that look at image classifiers on streams of video to check if classifiers generate the same predictions consistently across time. And you have even sort of these nice combinations between natural and adversarial examples where you just find images that are generally hard for classifiers, where we're not adversarially modifying the images, we're just finding images that happen to be hard pretty often. Now, there's a lot of these papers, and so I'm just going to focus for the talk on just this one, just because I think it sort of nicely captures what this field is doing. And so this is a paper out of Berkeley from a couple of years ago that what they do is they generate a new ImageNet test set. They go through all of the steps to try and just, the ImageNet test set was collected at one point in 2009. And they just go through all of the steps that they can in order to resample a new ImageNet test set. And they try as hard as possible to do exactly the same thing the original ImageNet authors did. They talked with the original authors. They made sure that they accounted for time bias. So they only sampled images that existed when this original test set existed. So for example, when you searched for phone, you're not going to get, all these examples of new modern smartphones. They tried to, they really did try to do everything possible to resample a new ImageNet test set. They followed the same process on Mechanical Turk to have images be filtered out. And as a result, what they end up with is a new test set where it's essentially identical in every way that you can imagine to the original distribution. And the question then is, how well do models do on this new test set? Like, what does their accuracy look like? And so what this paper found is it turned out that there's a consistent drop in accuracy onto this new distribution set. And so what I'm showing here is a plot where on the y-axis, on the vertical axis, what we have is the new test accuracy. This is on this new data set, this newly sampled ImageNet test set, which they called ImageNet v2. And then on the x-axis is the original accuracy on just the original ImageNet test set. And what you find is that classifiers have a consistent drop across the board, and they fall all very nicely on this, red line. The black dashed line here is perfect, no accuracy drop. And so a classifier that has, 70% accuracy in the original test set, it turns out, actually maybe will only have 55% accuracy on a new test set. And so this is sort of a very interesting finding this paper had, was that for some reason, there's something which makes classifiers do worse on this new data set. Okay, so the question is, what? And so this paper proposes a few possible things that could have happened. The first thing you could think is, maybe it's just a harder data set. Maybe despite them trying as hard as possible to make it the same, maybe it's just harder. Turns out the answer there is no. Humans fall exactly on the line. Humans do just as well on the new test set as the old test set. So it's not harder. You can maybe imagine that what it's doing is there's some kind of adaptive overfitting. So what adaptive overfitting is, we've been using ImageNet for the last decade, where people constantly train on the same models. And so you can imagine that we would somehow, accidentally overfit to the ImageNet dataset as a result of constructing models that work well in ImageNet. But it's not adaptive overfitting either, because if it was adaptive overfitting, what you would expect to see is that accuracy on the original distribution should go up, but accuracy on the new distribution should flatten out. This was what overfitting would mean. It would mean that we'd be doing better on the data set we currently have than the data set, and we sort of keep on getting better than whatever new distribution we have. But there's a very straight line here. There's no indication that we're overfitting to ImageNet. We're just sort of consistently doing worse on this new data set. Okay, so not adaptive overfitting. So what's left basically is distribution shift, which is kind of a cop-out for just everything else. Something about this data set is different. It was sampled at a different point in time. Despite the authors trying, there just must be something which is different about this data set in order to explain this gap. Okay. So this is what this original paper has done. And what we come and do is try and answer the question, are there any ways to increase the robustness against this or other kinds of natural distribution shift? Now, this is a very hard problem, and we don't think that we know how to answer it. So instead, what we're going to do is we're not going to try and solve this problem directly. We're just going to try and analyze a bunch of data and look if any existing approaches that are out there in the literature are able to solve this at all. Because there are a lot of papers that claim to have robustness improvements against synthetic or some natural distribution shifts. And so we just create a big giant grid where on one side you have all of the natural distribution shifts you can imagine. On the other side, you have all of the models that you can imagine. And we just run all of the models on all of the distribution shifts and try and see what interesting data we can pull out of this. Okay. So in order to formalize robustness, I'm going to have to make one definition for you of what I'm going to call effective robustness. And this is sort of the key definition that we make in our paper. And what effective robustness is it's how much better you do than you should expect given when you control for your original accuracy. So again, I'm showing you the same plot here, where on the x-axis, you can read this as the ImageNet versus ImageNet v2, but you can think of this more broadly as the original test set is on the x-axis, and whatever new distribution shift we have is on the y-axis. And there is some line of best fit of how individual models do. So models that are around 70% accuracy on ImageNet end up roughly around maybe 56% accuracy on ImageNet v2. If you're at 80% ImageNet accuracy, now you're at 68% accuracy on ImageNet v2. And there's a relatively controlled fit here. What effective robustness means is how high above the line you are. So importantly, if I have some model that's here, if I travel along the line by making the ImageNet accuracy better and the ImageNet v2 accuracy better, clearly this is a good thing. Like, more accurate models are better, but for our definition, it's not any more robust than you would have expected when controlling for the original ImageNet accuracy. And so this is a problem we find that almost all papers in the literature currently make, is they claim to be more robust, but they're only more robust because they have higher accuracy to begin with. And so in some sense, it's not surprising that it's more robust. They haven't so much come up with a robustness intervention to increase the robustness of the model as they have come up with a way to train more accurate models. And again, this is a good thing. More accurate models are good things, but it's disjoint from having more robust models. We would also like to be able to just close this gap because, importantly, going up and to the right is not going to have, eventually we'll have perfect models and we'll have 100% success rates. But as far as this plot is concerned, going up and to the right is not going to just completely close this gap. We would like to be able to move up above this line. And so, yes, so we, instead of being able to go that way, we would like to be able to go up and say, now we have gained some effective robustness. All right. So we analyzed basically all of the models that exist, something like 200 models on something like 100 different forms of distribution shift. I think it was maybe 1 billion different images we fed through ImageNet models. It's just a huge data set. It's all available for download if you want to. So I'm sure there's more interesting data in it. But what helps? What's the sort of the high level piece of information? And basically what we find is very little helps. So here we have the same line that I'm showing you earlier. All the points in blue are the standard models that I showed you before. But now I'm adding on some models in brown and some models in green. The models in brown are papers that claim to have some robustness intervention. They train on noisy images. They try and get, they train on adversarial examples. They have something in their network that they think is more aligned to human perception, and they claim that their models are more robust. And for the most part, they might be a little bit more robust, maybe a percentage point more or two, but they don't really do anything significant. The other models I'm showing are the models in green, and these are the models that have no robustness intervention per se, but are just trained on a lot more data. So for example, this point here in the middle that I've highlighted is Facebook's model that is trained on 1 billion images from Instagram. And the model in the upper right is the recent noisy student model that Google has trained on 500 million images. And so by training, as opposed to maybe the million images you see normally on ImageNet, you train on 500 times as much or 1,000 times as much data, you can somehow get like a percentage point or two above this line. But for the most part here, not much helps. And this was a story that we had in the paper. When we wrote the paper, this was true. When we gave the talk at NeurIPS, this was true. Sort of very excitingly, within the last couple of weeks, OpenAI came out with this really interesting model called CLIP, where they trained, I don't want to get too much into the details here, but they trained a new model on even more data. And their model sits here. And it sort of halfway closes the gap. And this is like exactly the definition of effective robustness that we want. This model does just as well as the normal ResNet on ImageNet, but it's significantly more robust to these kinds of distribution shift. And I think this is sort of a very interesting new direction that we're just starting to think about. The fact that this model does so well was, this model only came out a couple of weeks ago, and so we're very excited to see this kind of thing. And so we may, have in the near future some kind of idea of how to solve some natural robustness from this models. But I think it's still very early, and so as always, there's always more papers coming out. So again, for the remainder of the talk, I'm going to be ignoring CLIP just because it came out after our work. But I think it's interesting to think more about what this could mean for the remainder of this talk too. So I've talked a lot, just sort of saying, presuming that this one data set generalizes, and it's not just, like a weird data set. And in our paper, if you're interested, there are the same exact kinds of plots where instead of showing ImageNet versus this ImageNet 2 paper, we compare against ObjectNet, and the same thing happens where everything falls on a line. Training on a lot more data doesn't get you so much better. Again, CLIP goes way above this line again. Or vidRobust, which is this video data set that asks that if you make a prediction at a certain time, then plus or minus a couple of frames where the object can't have changed much in a couple of frames, you make the same prediction. Again, training on a little more data or training on a lot more data helps a little, but not significantly. And so it's not just a weird data set. Like, this is something that generally holds true across data sets. And it seems like models are very hard to train in this robust way. The last thing that we look at in this paper is if it's true that making models more robust to synthetic distribution shifts also makes them more robust to natural distribution shifts. And so if you remember, the distinction I drew here is that synthetic distribution shifts are things that are like, you can write a program to generate. So maybe this is like applied JPEG compression, add pointwise noise, generate adversarial examples, rotate the image to be some weird angle, color adjust, contrast adjust, these kinds of things that you can write down. And natural shifts are these shifts that actually happen in practice. And so there are lots of ways that people have found to make models robust to synthetic distribution shifts. And so it's natural to ask, is there some correlation between the synthetic distribution shifts and these natural distribution shifts? And for the most part, the answer we find is that no, this is not the case. So for example, one of the ones that we look at is ImageNet C, which, as I was saying, does brightness and contrast and JPEG and multiple kinds of blur and multiple kinds of noise. And what you find is on the y-axis here, we're looking at the effective robustness. Again, this is how much better you do than you would expect given the original accuracy. And on the x-axis, you have the average common corruptions. This is the synthetic robustness. And models that are more robust against these kinds of synthetic common corruptions are on the whole not more robust to natural distribution shifts. And so the answer, and so what you notice is these models they can be more robust to synthetic distribution shifts, but that doesn't actually correlate with any real robustness on natural distribution shifts. And so on the whole, this is what makes these things very hard, is that it's hard to figure out how to do better on these natural distribution shifts, in part because getting training data for them is expensive. You can't just simulate it in this way. You actually need to get more real data, and doing that is not easy in many ways. So to briefly conclude then, basically, if you want to increase robustness, it seems like you can train on more data, which helps a little bit, but not a lot. Or if you know what kind of data you actually care about, you can train on that. And this is essentially what the best defenses to adversarial examples do, I'll just say, is they just train on adversarial examples until the thing converges. And in practice, this is basically all we have. Like you could do one, or you can do two, or you could just train on distribution shift you care about, or just it really seems like the best way to get robustness is just to train on what you actually care about. And this is fairly unsatisfying for a solution and something, because we want these classifiers to be robust. They're just not all that robust today. And again, this is what makes this field difficult, is these kinds of this robustness is something that we really do want classifiers to have, but as of now, we don't yet have it. Whether or not we're talking about these adversarial worst case kinds of shifts, or these kinds of natural distribution shifts that are just completely benign, people taking pictures of objects in their homes. And so with that, the title of the talk happens to also be the conclusion, where neural networks just are still not robust. We're getting there. We've made some very good progress, especially recently, on these natural distribution shifts. We're not quite there yet all the way. And I'm excited and hopeful that in the future we'll be able to do that by working hard on this problem. Thank you, and I'd be happy to take any questions.
Thank you. Any question?
I'm Fabio, Andrea. Can I do a question?
Yes.
Go ahead.
Yeah, thank you. I'm Fabio Rolli from Italy. Thank you first, Nicholas, for really an interesting talk. My question is a general question about your view on the next step in adversarial machine learning. My question is, do you think that the big issue of the security of machine learning can be really solved from inside of machine learning, or given the current paradigm of machine learning based on learning of statistical correlation, you should accept this limitation and make aware the practitioners that the security of machine learning must be solved outside of the machine learning component, if possible. Is clear enough, my question?
Yes. No, yeah. So just to rephrase briefly, should we even be trying to solve this, or should we just accept the fact that statistical learning is going to pick up on something that is unintended, and this is just how life is going to be, and we should put the emphasis on some kind of control loop to try and solve the problem out externally? That's what you were trying to figure out?
Yeah. My question is that in some sense, and you mentioned this in one of your last slides, in the end, to have more robustness, you need more data, if it's possible, or you need a model of the distribution shift that bring us back to the 80s, to the fundamental problems of statistical machine learning.
Yeah, I agree with you. I think that there is, I have hope that things might get better. I don't have any evidence that this will get better. But, I wouldn't have thought, 10% of the things that we can do today would have been possible a decade ago. So I have hope that in another decade, we might be able to solve some of these problems. I don't know how, but I'm hopeful. In the meantime, I definitely think that we should make sure that people who use these systems are aware of these kinds of problems and don't rely on them in situations where they're not reliable. Any self-driving car, for example, that uses a machine learning system, I hope has a classical control loop that will make sure it doesn't do obviously silly things if presented with a person that it has never happened to see in that position before. And I think in some sense, this is inevitable that we're going to need to have these classical human designed algorithms for the foreseeable future, just because at least then we'll know that what we've done is correct in the settings that need to be safe. There are lots of settings where things don't need to be safe. If we have some bird watching app for people who want to know like exactly what kind of bird they just took a picture of in some forest, it's fine if it makes the wrong error. This is not like no one's going to die as a result of it. This person might be unhappy that they took a picture of the wrong bird, but everything's fine. But in the settings where we need things to be robust, I do think you're right that having some kind of make the operator be aware that these systems might misbehave and to have some in the loop thing is, at least for the time being, probably the most prudent thing to do.
Okay, thank you very much. Very clear. Thanks.
Yeah.
Any other questions? If not, I have one, or a bit of a comment and question together.
Sure.
Okay, you make a very clear distinction between the overfitting bit and the distribution shift, which from my point of view are sort of almost two faces of the same metal in the sense that distribution shift, it's just a sort of meta higher level class variability or class invariance, in the sense that there are things that happen in the real world that systematically can change the distribution, and actually you could just factor them out and see the distribution as a much wider distribution, including all of those. Of course, that makes the whole distribution much harder to sample, and that where you get the idea that you want to sample for the distribution shift that you know about. My point is, do you think you can actually try to solve for learning or sampling in that much wider sense? And why is, and if that is at all possible, why is giving more samples only increase that so little the effect? Are they just sample from a single set of invariants, a single set of distribution shift? Is it?
I don't think I completely get the question. Could you?
Oh, the point is, from what I see, distribution shift is basically just new ways, new models by which you can, new class invariants, new things that you can vary in the way you acquire information from the class. That are there, they do exist, and the actual class, class appearance distribution is just much wider than we had, because we have this other different ways things can vary. But if that were so, you would actually be able to sample with a lot more samples, sample that as well. And but then you show that that's not the case, because even images with much models were trained with a much larger data set, even huge data set, increased performance, but not robustness. Can you comment on that? So is it really something fundamentally different in having this model shift than just having much wider than expected class distribution? Or is it just a problem of how those samples were obtained?
Yeah, no, this is a very good point. In the limit, a classifier that had 100% accuracy on a sufficiently large data set is not going to have problems with distribution shift, as long as you have the data that captures the distribution shift that you're going to see. The question is, I think, for classifiers that are imperfect, that get something like 90% accuracy, that just means that on aggregate, they're getting 90% accuracy. And there might be some modes of the data where they suffer more than other modes of the data. And where it suffers more than others is unclear. You might expect that it just gets 90% everywhere. And this would be good. This is what we would like. But it seems like that's not the case. I do think that sort of, if I were to wildly speculate, if you could come up with a diverse enough data set, diverse meaning not in like the diversity sense, but in the representative sense, like a data set that represented each distribution equally, I do think that this data set would be robust to these kinds of natural distribution shifts. I think that part of the reason why OpenAI's recent CLIP paper might do so much better than what we've seen before is that they didn't gather images like most other papers did, trying to do like Imagenet classification. Their paper was much more a scrape the internet for all possible images and just learn on everything that we can get our hands on. And I think this contributes significantly. Like Facebook's Instagram thing, they trained on 1 billion images, but they only trained on images that had very particular tags associated with them. And so having 1 billion images is better than having 1 million images. But if all of your 1 billion images are the same kinds of images, having more of them in some sense isn't helping you all that much. Whereas the images that OpenAI has had with this new model, of course, like we don't have access to exactly what these images are. And so I think there's more research needed, but I think it's entirely possible that what's happening here is that because the data set is so much more representative of the images that we're going to test it on, that that things are fine. This is my hypothesis, but I have no evidence for this right now.
Thank you. Other questions?
I have a question.
Yeah, go ahead.
Thanks for the talk. So based on the last slides, I'm thinking then what you mean is that probably data augmentation is not, well, is giving a negative effect on robustness, because you said that there is this trade-off between synthetic data versus natural data. And so I'm thinking that probably this is something that is not really helping to our more robust
yeah. So I'm not going to say that data augmentation is negatively correlated. I'm just going to say it's not positively correlated. So what it seems. So for example, among these points here, some of these points were trained with data augmentation explicitly trying to do well on common corruptions. And training them to do much better on common corruptions doesn't make them do that much better. It doesn't. It's not like you'll notice there are more points above the line, above the 0 point on Imagenet v2 than below. Like on the whole, things don't hurt. They just don't help that much. If training with data augmentation helped a lot, you would expect, more than 2 percentage point gains of effective robustness on Imagenet v2. But basically nothing gets more than 2 percentage points. Again, this plot is excluding CLIP, but yeah.
Yeah, and my last question is, what are your thoughts about implementing things like causal inference to add things that are not in the data?
Yeah, no, this is, I guess, goes back to the first question of, can we sit down as humans and think and design a system that will use machine learning where it's important, and will say, here is some causal inference, so handcrafted stuff that's good. I think that yeah, again, in the limit, I have no idea how good machine learning will be able to do. You know, some people say that it's going to do, you know, solve everything, and I'm not sure if I'm that optimistic, but it's been more effective than I would have guessed in the past, and I think the possibility that it will, again, in the limit, might do better is I don't know. I don't know what odds I would put on it, but I think it's conceivable. But yes, again, for the time being, some kind of causal inference doesn't seem unreasonable. I think for these kinds of distribution shifts, I don't know how I would specify something like this. But I think it's interesting to think about. I think it's not as easy as just saying, you know, we'll just apply causal inference and solve everything, or any other handcrafted thing. Like, we have to remember the reason why we decided to go with neural networks, you know, as the community for the last decade is because people tried for 20 years to do, you know, handcrafted, good old-fashioned AI, and it doesn't work as well as neural networks on most of these tasks.
Thanks.
Other questions? Okay, appears not. So let's thank Nicholas again for for his wonderful talk and his being here. And I guess we'll just let you go and rest now.
Yes, no, thank you very much. It was great to come talk.
Thank you. And we'll meet again in about 30 minutes for the discussion session.